Okay, so hello everyone. Should I wait? What? Can you start it? No, what?
I think he's said he's going to tell everyone to come in.
I see. I
Very
see.
optimistic.
Can we start? Okay. Okay, so welcome to the first session of the last day. We'll have 6 talks. First one is by Steve Haneke. Welcome, Steve.
Okay, thanks. Yes, so I'll talk about universal rates for ERM in the agnostic case. Okay, so the setup is kind of standard statistical learning. We have some distribution P. This is the agnostic case, so there are no assumptions. If you imagine you have an IID data set, these are just XY pairs. And we'll just talk about binary classification here. And then we'll specifically study the ERM learning algorithm. So let's let H hat n denote what happens if you run ERM on data set of size n. So ERM just returns the concept in the class that makes the fewest mistakes. So that, I guess implicitly here there's a concept class, H. Then the question we're going to study is what kinds of rates of convergence do you get for the expected excess error rate? So the expected error of ERM minus the best error in the class. How quickly does that go to 0 for all distributions? So we're interested in the asymptotic rates. There may be, for instance, constant factors and things of that sort that depend on the distribution P. The sort of high-level summary of what we find is there's 3 possibilities for each concept class. You can have exponential rates. That happens if and only if it's a finite concept class. You can have little o 1 over root n rates. That happens if it's an infinite concept class with finite VC dimension. Or you can have arbitrarily slow, at least arbitrarily slow rates. So there are some classes that are just not learnable by ERM, meaning it's not even consistent. In the paper, we also have some more refined versions of this where we talk about H star dependent rates, H star best in class, and also rates that are Bayes dependent, where Bayes, the Bayes classifier doesn't have to be in the class, but we can define rates of convergence that are specific to each concept, each possible Bayes classifier. But yeah, see the paper for that or talk to me offline. So that was sort of the high-level summary. Let's formally introduce things. So here, a learning problem is just described by a distribution on x cross 0, 1. Concept class is just a set of classifiers, functions mapping the instance space x to 0, 1. And ERM maps any n xy pairs to a concept in the class that makes the fewest mistakes. And we're interested in its error rate, meaning the probability that it makes a mistake on a fresh xy drawn from the distribution. And yeah, as I said, we're interested in the rates of convergence of the expected excess error rate, so expected error rate minus the best in class error. The classic theory here studies the uniform rates. And here, so for any sample size n, in the worst case over distributions, the expected excess error rate is precisely square root VC dimension over n. In contrast, what we're going to be interested in is like allowing distribution dependence in each so for each distribution, there'll be some rate of convergence, and we're interested in what are the rates of convergence that can hold for all distributions. And the 2 main cases in that list were exponential and little o 1 over root n. So just to unpack what those mean, an exponential rate means that for all distributions, the expected excess error rate goes down exponentially fast, maybe with a constant in the exponent that depends on the distribution. And it's exactly exponential if there's some distribution for which that's sharp. A rate of exactly, a rate of little o 1 over root n comes if the expected excess error rate goes down faster than 1 over root n, but it's exactly little o 1 over root n if for all functions that are faster than 1 over root n, it doesn't, there's some distribution witnessing that it doesn't go down that fast. So that sort of the best you could prove is that all distributions have little o 1 over root n rate. And this is what we proved, and as I said before, it's the exponential or 1 over root n, depending on cardinality and VC dimension. I'll just sketch out a few of the proofs. The exponential upper bound is pretty straightforward. If you have a finite concept class, then if we let epsilon denote the smallest non-zero excess error rate witnessed in the class, that's a distribution-dependent quantity, and it's non-zero, then the expected excess error rate is bounded by, of course, the probability that the excess error rate's bigger than 0. But if it's bigger than 0, then it's at least epsilon, because that's the smallest non-zero gap you could have. And then we just Hoeffding and union bound kind of standard arguments says the probability that any, so if it were bigger than epsilon, then there must be some concept whose empirical and true error rates differ by more than epsilon over 2. And just Hoeffding and union bound say that won't happen with probability, except with probability exponentially small. So that's our exponential rate, and you see that epsilon that shows up in the exponent is the distribution-dependent constant. The fact that if you have infinite cardinality, ERM is no faster than little o 1 over root n is a little more interesting. So here we use some structure that this implies. So in a paper I presented at last year's Colt, I showed that any concept class with infinite cardinality admits an infinite eluder sequence. That's a sequence of xy pairs such that for any t, there's some concept ht in the class that is correct on all the points up to time t, but incorrect at time t. That's an infinite eluder sequence. And we'll use that structure to prove a lower bound, basically define a marginal distribution on those x's. It's just some decreasing sequence, decreasing quickly enough. And then for each one, we'll set up essentially the agnostic kind of lower bound construction that we usually do for just 2 points, but we'll do it for each point in the sequence, where we set the probability of y given x to be just epsilon, some epsilon t in favor of the eluder label. And then we know, if you don't have like 1 over epsilon t squared copies of that example, you can't, ERM might pick the wrong one. And so generally, for some nt that's like 1 over the probability of that point, epsilon t squared, you might pick ERM might pick the wrong label with some constant probability. And that turns into like a square root pt over nt lower bound on the expected excess error. And if you play around with how you set those epsilon t's relative to pt's, you can witness anything that's growing or decreasing faster than 1 over root n as a lower bound there. The fact that finite VC dimension implies ERM has a faster than 1 over root n rate kind of follows from some tools that are known and an interesting new topological argument that, okay, so if we let h of epsilon be all the concepts that have excess error at most epsilon, it turns out that for the worst case over all those concepts, or let's say for all of those concepts in h of epsilon, there's some concept that's much better. Let's say instead of epsilon, it's epsilon squared excess error, for which it's actually pretty close. So all concepts in the h of epsilon class have some really good concept that's pretty close to it. And as epsilon goes to 0, that gets closer and closer. And this follows from some sort of pseudo-compactness kind of arguments about the concept classes. Now we know ERM from classic theory has, at worst, like a square root, let's say log n over n, kind of excess error rate, and that means that there's some concept with that squared excess error rate that's actually pretty close to ERM. And so if we just plug that into a uniform Bernstein inequality, we can get that the expected excess error rate is bounded by like the square root VC over n times this distance to that closest really good classifier times log 1 over that, and that'll be little o 1 over root n just by this lemma. For the other case, that VC infinite implies ERM has at least arbitrarily slow rates, it's a lot like the eluder sequence argument from before, except it turns out having infinite VC dimension implies you have an infinite VC eluder sequence. That's like, imagine a sequence of blocks of examples of increasing size, such that the concepts that are correct on the first k blocks, VC shatter the k plus first block. And then we can use that with similar arguments to the eluder sequence, but now since we have these shattered sets instead of just 1 point, it sort of gets harder and harder as you go down the sequence, and that could witness an arbitrarily slow rate. Some open problems. What are the rates for multi-class learning? In the uniform rates, we know you can just replace VC dimension with graph dimension, and that gives you the uniform rates. Turns out that's not true for universal rates, and so it'd be interesting to try to characterize that. And it's probably maybe directly in terms of eluder and like graph eluder sequences. And then what are the optimal rates for general proper learners? We know at least that it gives a different set of possibilities. Thanks.
We have time for one question, I think. Anyone? Question? Okay, so maybe I'll ask one.
Okay.
So what do you know about the proper learning case?
Okay, so I mean, we have like an example where it's not, where this is not the right answer. Singletons on the natural numbers, let's say. There's a proper learner that gets an exponential rate even though that's an infinite cardinality class. Just sort of default to the all zero unless you have strong evidence that it's not supposed to be all zero.
Okay, thanks.
Which one is yours? Oh, sorry. It's that one. Yeah, perfect. Okay, I have this.
Okay, so our next speaker is Justin. Welcome, Justin.
Yeah, thank you. So today, first of all, this is joint work back from my PhD with my advisors, Aditya Ramdas and Stephen Wu, and I'm just going to be talking about a single self-normalized but general concentration inequality. So before diving into the framework and the results, I'm going to start by motivating what is self-normalized concentration by contrasting it to maybe more standard classical approaches to concentration. So for deriving classical concentration inequalities, one would typically assume I have access to maybe n IID observations. I let Sn be their partial sum. I fix some failure probability between 0 and 1, and I want to print out a bound that depends on n and delta, such that the probability that the distance between Sn and its mean is more than un delta is bounded above by delta. A really standard example, if I know that each of my random variables is bounded in some interval, almost surely, then what I'll get is I can take un delta to be sort of this standard Hoeffding bound. And so concentration inequalities such as these are like the workhorse of a lot of learning theory, a lot of statistics, but they have a lot of shortcomings. Maybe problems is not the right word. But first of all, the dependent structure is sort of a very strong assumption. These concentration inequalities work for independent observations, but what if I have dependent data, or data generated through a human-in-the-loop process? Second of all is validity. Typically, we assume a fixed sample size. But what if we're doing A/B testing or something like that, and we want bounds that are valid at data-dependent stopping conditions? Or equivalently, we want time-uniform bounds. And lastly, and sort of the key focus of this talk, is variance. A lot of these classical concentration inequalities depend on the sample size. And so the question is, what if we want bounds that depend on some other measure of the variance, maybe like an adapted covariance, a predictable covariance, or something like that? Moreover, what if we normalize the growth of the process by its variance? This brings us to what is time-uniform self-normalized concentration. The heuristic setup is I'm given a process Sn and Rd, some matrix-valued measure of variance, Vn. These are like positive semi-definite matrices, a confidence level delta, and I want to print out I want to sort of get a function u that depends on the matrix and the failure probability, such that the probability at any point in time, when I normalize Sn by its variance, the norm of this thing is, with like high probability, it's less than or equal to this bound I print out. So let's just parse each of the parts here. Well, we have the existential quantifier over n. The bounds would be time uniform. We're normalizing the growth of the process by its own variance. The bound depends on the variance. And we'll see in the sequel, these bounds are going to hold far beyond IID settings. And just pictorially, what's going on, the process evolves in Rn, here in R2, and then we basically try to put it in an ellipsoid that sort of expands based on how much we explore each direction. Okay, and so before we present our result, we'll talk about the key assumption. And so we call this the multivariate sub-psi assumption. It's based on some work from Howard et al. In the scalar case in 2021, 2022. It basically says, I'll say a multivariate process Sn is sub-psi. Think of psi as the CGF of a random variable with variance proxy Vn if the following holds. For each lambda in some range and each direction in the unit sphere, I can define some exponential process that has sort of two competing forces. We have lambda times the projection of Sn onto direction nu. This thing is something we expect to be increasing in magnitude over time. And we push down by psi of lambda. This is the CGF, so it accounts for the heaviness of the tails, and then the projection of the covariance onto the direction nu. And so we define this exponential process, and we say that Sn is sub psi if, for any nu and any lambda, we can find a non-negative super martingale, it should be lambda nu, that dominates this process. Why is this a reasonable condition? Well, we derive most standard concentration inequalities from Markov's inequality. If we want time uniform and self-normalized things, we typically turn to Veal's inequality. This is just a time uniform variant of Markov's inequality. Okay, and so this is sort of a technical definition, but just to check that it's reasonable, we should do a couple examples. So first of all, we'll see that with this definition, we can recover assumptions based on CGFs. This is like the no-brainer test we should have. So if Xn have conditional CGFs bounded above by psi lambda when I project onto any direction, then this process, which I push down by n times the CGF, is actually itself a super martingale. And so my process is sub psi with variance proxy n times the identity. This is not a super interesting example. In a longer talk, I would do 3 more examples, but I'll just do one more. Suppose I have random variables x1 through xn, and all I'm going to assume is that they're conditionally symmetric. They don't have even a well-defined mean. Then you can actually show that this process is sub psi. And so what we're doing instead is pushing down by the adapted covariance projected onto a given direction. So not only is this like recovering classical notions of tail conditions, but it's actually extending it. And there's other examples as well. There are Bernstein examples you can do with like sub-gamma tails. And so the question is, given this setup, what sort of rates should we expect? Well, the most naive thing one could do is like do a Chernoff bound in Rd. So if I have IID random variables and they have a corresponding bound on their CGF, I can get a bound that up to constants roughly looks like the following. So if psi is the CGF of the random variables, psi star is the convex conjugate, you can show using standard techniques like a covering argument that Sn over root n, which is like a naive measure of variance, is less than or equal to square root of n psi star inverse, something that depends on the dimension plus log 1 over delta over n. In the setting of like sub-Gaussian random variables, this simplifies greatly. It's just square root log 1 over delta plus d. For something more heavy-tailed like sub-gamma, this is like square root log 1 over delta plus d, plus a term that vanishes as my sample size gets large, or as the central limit theorem starts to kick in. So the question is, we have an arbitrary measure of covariance. Can we like find some appropriate function of the covariance matrix, maybe a trace, a determinant, maximum, minimum eigenvalue, such that we can just plug that in to the Chernoff bound? This would be the ideal situation. The answer is, unfortunately, you can't do it. So even in scalar settings, if I want time uniform bounds, I need to pay a doubly logarithmic price, in the scalar case, just Vn. But what's really interesting is once you go to 2 dimensions, there are actually processes that sort of asymptotically have the norm, like the self-normalized norm grows as d log kappa n. So in general, we can't even hope to get log of Vn. So the question is, can we get the next best thing, which is maybe a dependence on both doubly logarithmic sum function of the covariance and then log of the condition number. Condition number is just maximum over minimum eigenvalue. Okay, this takes us to the main result. What is the main result? Well, suppose I have a d-dimensional sub-psi process with variance proxy Vn. So sub-psi, again, is roughly like the CGF of the increments. Then you can show that with probability at least 1 minus delta, simultaneously for all n bigger than or equal to 0, the self-normalized quantity is less than or equal to something that has, it looks a little complicated, but we can parse it term by term. It has doubly logarithmic dependence on the maximum eigenvalue. It has a dependence on d times the log of the condition number. Of course, it has dependence on log 1 over the failure probability. And then lastly, it has, maybe this is a little weird at first, but dependence on the minimum eigenvalue. And so we can sort of parse this in a bit more detail. First of all, the appearance of the minimum eigenvalue is very natural, I would say. Why is it natural? Well, the sub-psi condition controlled the growth along any direction we could project onto. If I don't explore some directions, then I can't hope to get sort of in the limit sub-Gaussian concentration. So what this is saying is I just need to, in the limit, explore all directions. And what this says is that basically, if my covariance matrix is well-conditioned, I'll get doubly logarithmic rates. Otherwise, I'll sort of revert to getting d log the condition number rates. And so maybe as a final point, we can specify the setting of sub-Gaussian processes for which there are some self-normalized concentration results known. So our result, in this case, simplifies to something quite nice. It just, the bound on Sn normalized by its variance is just doubly logarithmic in the maximum eigenvalue, d log the condition number, and then it has log 1 over delta. And so other bounds, particularly those commonly used in the multi-arm bandit or like the contextual bandit literature, take a slightly different form. They shift the covariance and then basically give you a bound that looks like log of the determinant. And so what's interesting here is that our bounds hold for sort of general psi. So they're much more general in terms of like what tail conditions they can handle. But even in the sub-Gaussian setting, the bounds are sort of totally distinct. In particular, if the covariance matrix is well conditioned, ours is actually tighter. But if it's poorly conditioned, the existing log determinant bounds might in fact be tighter, which we find very interesting. And maybe as a final point, we've been hiding constants throughout the presentation. There's a lot of, if I were to put the actual bound up, it has a ton of tuning parameters. And so the question is, are we hiding something nasty? Are there very large constants? And so I didn't even optimize the constants. I just picked some small values. And the bound actually works out quite nicely. We have a factor of 3 out front. This could probably be improved by tuning things more appropriately, but then it just reduces to, log gamma max, then log the condition number. Anyway, that's the presentation. Thanks for listening.
Okay, thank you. So, any questions?
Thank you. Just a quick question. Sorry, I'm here. Should I proceed? Yeah. A quick question then. Sorry, I'm here. No.
There, okay, cool.
Here.
Oh,
yeah.
sorry.
Yeah, about your very last slide. So can you display it again? So what is the best constant we could reach, and is it possible to have it
here.
with a 1, say, instead of the 3, at the price of what inside of the square root?
Yeah, so, I'll talk into the mic. So actually, the way we sort of evaluate tightness in the paper is we look at sort of, can we prove asymptotic laws of the iterated logarithm with a correct constant? And so in the scalar case, we get exactly the right constant. You can sort of sequentially tune the bounds such that, if you do some careful arguments, I get the right thing in the limit. In the multivariate case, we get within a constant fact, the law of the iterated logarithm there that we prove is there's a lower bound of d log kappa, square root d log kappa. I think we might pay a factor of 2. So maybe there's some additional tuning that can be done there. But it's not, the bound's not too loose in that sense.
Yeah, hey. So it wasn't clear for me, to me from the presentation whether this is just a standard L2 norm and what other norms you can potentially handle.
Yeah, so this is just a standard L2 norm. We don't look at other norms in the paper. My guess is you could likely, in any place we've done Cauchy-Schwarz, try to do something like a Holder's inequality instead. But I'd have to think more about what exactly is happening there to see exactly what rates we'd get or if they're actually reasonable.
Thanks.
Cool. Okay, so let's thank the speaker again.
So this is what I speak into, right? Oh, okay. And probably do something like that. And what? This one. This one. right? This. Okay. And can it point?
Yeah.
No. Oh, this one points. Oh, great.
Okay, so our next speaker is Bogdan Chornomaz. Welcome, Bogdan.
Hi, Shai. Okay, so I'm gonna be talking about this like new dimensions that we came up with. What? That we came up with. I just want to take a. Okay, I just want to be able to look into the screen. I'm going to be talking about these new dimensions that we came up with, which we called spherical dimension. And roughly speaking, like if I would to give another informal name, it would be like this one, using Borsuk-Ulam in learning theory. So recently, maybe like for 2 years, me, together with a bunch of other people, Steve, Shai, Tom Vaknin, not here right now, and some other people, we have been using like topological tools applied to problems motivated by ML, and we got some success with that. And we wanted to sort of find a common denominator in our methods, and these dimensions that we suggest is we think about it as this sort of a common denominator. Okay, so let's look at this beautiful picture. It's sort of like a mind map of the stuff that we have. In the center, do you see this red dot? When I point it, you can see it, right? Okay. So SD is the spherical dimension. Okay, that's all those guys. They are parameters of the class. So we have a class, and it has a certain spherical dimension. And those three guys up there, it's like a typical use case, our typical use cases. Normally, we use spherical dimension to get lower bound on parameters of interest, which have some meaningful learning theory interpretation. Okay, so for example, maybe it's better to start with this one. So least replicability number. Roughly, it says how stable your learner can be on this particular class. Being stable means that you would only have some number of like reasonable hypotheses returned for any particular distribution, right? And as it turns out, it's lower bounded by spherical dimension. Then you have like an SCO dimension, stochastic convex optimization dimension, as we call it. And roughly speaking, if you want to design a learner by reducing to a problem in stochastic convex optimization, then again, you would need your dimension of the stochastic convex optimization to be sufficiently big, again, lower bounded by SD. Finally, this VC extra is if you want to wrap your class into extremal class, which we often think of as like good classes from the perspective of, for example, sample compression scheme conjecture. But then again, it turns out that you need to sort of go above spherical dimension. Okay? On one hand. On the other hand, there are some natural sort of combinatorial parameters that lower bound spherical dimension in its own term. For example, VC lower bounds it, which is probably not surprising, but also VC star being like dual VC dimension. It's often interesting that indirectly this way VC star lower bounds these parameters, and VC star can be exponential in VC. Okay, so all those three parameters, they can be exponential in VC as a consequence. Okay. Here we have upper bounds, and it's like we really don't have them, right? So we have like this big question mark. And that's sort of a big question for us, whether we can bound a spherical dimension with a function of VC dimension, with any function. And what we know is that it can be up to VC times VC star for different ranges of VC and VC star, okay? But all in all, it's a big question mark. We don't know any upper bound on SD in terms of VC. However, recently, another group, there is a guy in yellow T-shirt sitting somewhere there. His name is Ari. Oh, okay, here he's waving, yeah. So recently they sort of were able to bound it with Littlestone dimension, okay? And then they bound, it works this way. So what they bounded this parameter, which I haven't mentioned yet. It's sort of, it's a little, yeah, I'm gonna talk about it later, but roughly is like if you want to disambiguate linear classifiers with margin, then you would need to have certain VC. And this wiggly line between them, it indicates that basically this problem and bounding VC, they are like, those problems are equivalent, like, hence sort of the lines go into both of them in both cases, okay? So that's like a rough map, okay? So lay of the land, so to say. So let's at least try to define, let's at least try to define what the spherical dimension is. And for this one, like basically it's like a main picture of, we are interested in our realizable distributions, but we are interested in realizable distributions as a set. And the central observation, which is sort of trivial, but somehow it's like a change of optics a little bit, that the set of realizable distributions, it forms a simplicial complex, okay? So so that's our class, it's like a pretty simple one, and for every function in the class, we have a simplex. That's a simplex corresponding to F, corresponding to G, to H, and to I, right? And our vertices, they are labeled examples, okay? And like taken together, that's how all realizable distributions look for this particular class, okay? And if sort of we process this simplicial complex representation, now we are interested in a particular part of this simplicial complex, namely the antipodal part. So some distributions, you can take sort of an antipodal distribution, which flips the labels. And sometimes you end outside of the class, but sometimes you end inside the class. And we are interested in the part of the, in those distributions for which you can take those antipodals, okay? And then basically the spherical dimension is the maximal n such that there is an antipodal map from a sphere, n-dimensional sphere Sn, into this antipodal complex, okay, into this antipodal part of the complex, okay? Here, for example, you can clearly see that it's like a circle, right, topologically. So here, this picture witnesses spherical dimension 1. But in general, there are like pretty classical combinatorial constructions which correspond to spheres witnessed by VC and VC star, okay? So for VC, for example, it's a boundary of a cross polytope. For VC star, it's a barycentric subdivision of a simplex boundary. Like, doesn't really matter like what they are, but those are like pretty canonical sort of things, okay? And now maybe like coming sort of to certain like results that we have, how we can use, for example, to this line, okay? What we established is for extremal classes, for example, like this class is extremal, just thresholds. You can have this complex that we are interested in, okay, the distributions, okay? But also you have what's called a cubical complex, and cubical complex is something that we used in our previous work regarding embeddings, okay? And the thing is, the cubical complex, it has much smaller dimension, okay? And what we've established is that for such classes, there is a thing called deformational retraction, which is roughly speaking a mathematical way of saying that the complex inside, it somehow like captures the structure of the big complex. And from this follows the bound. And I have some more, but I've run out of time, so yeah, let's wrap it up at that. Okay, questions?
Okay, thanks, Bogdan. So, any questions? Good.
great presentation.
Hi, thank you.
I was wondering if you have a best guess or a best hope for spherical dimensions relation to VC and VC star.
I mean, I don't know, this bound VC times VC star, it seems very like hopeful, but then when it comes to proving it, I'm not sure. I don't know, I mean, it's, it can go both ways, and I think both ways could be like pretty hilarious, I don't know.
Thank you.
I would try to prove that it holds, but like, you know, in the process of proof, it can go sideways.
Okay, any other questions? If not, then thanks Bogdan again.
Thank you.
Who is our next speaker? No, okay.
How do I open it up?
So which one is yours?
Akbari.
Blackberry Final Slides, perfect. Oh, what is that? No. No. There. Don't worry, everything is fine. You know how to use them. Well, the pointer. Yeah, here. You know how to use this?
Oh, perfect. Okay.
And if you want to hold this button here.
Thank you.
Okay, so our next speaker is Sayed. Welcome, Sayed.
Hey everyone, my name is Sayed. Can you guys hear me? Okay. Hey everyone, my name is Sayed. This is a work that I did at the University of Michigan with Professor Matthew Harrison Trainer. So today we're going to talk about binary classification theory with pack learning. And first, just some quick notation. So our feature space is going to be the natural numbers. This is because we're dealing with computability. You can imagine this being like the Gödel encoding of any actual countable feature space that you're concerned with. Because we're dealing with binary classification, our label space is just going to be 0, 1. A hypothesis then is just some function from the naturals to 0, 1. A hypothesis class is just a collection of such hypotheses. So, and then just to get everyone up to speed, real quick, we say a hypothesis class is pack learnable if there exists a learner such that on most training sets, so that's like probably, it can learn the binary classification with best generalization error. So now, traditionally, there's two settings of pack learning. So there's the statistical Vapnik-Scherner, basically the statistical VC theory. So here, the pack learner can just be an arbitrary function. It doesn't need to be computable or anything. And this version of pack learning has a nice characterization through finiteness of VC dimension. There's also variance efficient pack learning. So this is where the learner has to be polynomial time computable. Today, we're going to be talking about this other notion of pack learning, which was introduced by Agrawal and others, which says that, okay, we're considering pack learning where the learner has to be computable, meaning that there has to actually exist some program that can actually do the learning, some program or algorithm. So first, we might hope, or one might assume that, okay, can we say that for every pack learnable class, it will also be computably pack learnable. So for every pack learnable class, that there actually will exist a program that can actually do the learning. And unfortunately, that is not true. And Agrawal and others showed that through a hypothesis class, through like a counterexample that looks something like this. So this is a hypothesis class that consists of a bunch of indicator functions. And these indicator functions are included in the class based on whether certain proofs prove certain other formulas of arithmetic. And this hypothesis class has VC dimension 2. So basically finite VC dimension, therefore it is pack learnable. However, they show that if there existed a computable learner, then basically they showed that there can't exist a computable learner using the undecidability of like proofs and like arithmetic. Now, guiding question. Now this leads us to ask, okay, so PAC does not imply CPAC, but in the normal course of learning theory, can we expect that if you have a PAC learnable class, it will also be computably PAC learnable? And now, this isn't a formal question because we're saying in the normal course of learning theory and when we're dealing with natural PAC learnable classes, can we expect them to be CPAC? So we can't hope to have a formal answer. However, in our work, we prove certain formal results, which we believe suggest that for many natural hypothesis classes, PAC learning and CPAC learning do coincide. And the technical tool we use is the on-a-cone technique from computability theory. But before I can explain that, I gotta build up a bunch of quick definitions so we can get there. So first, okay, for a hypothesis class to be computably learnable, first, the computer should have some sort of access to the hypotheses in the hypothesis class. So it should be able to computably list or computably enumerate all the hypotheses in the hypothesis class. And then also, for each hypothesis, to be able to actually run it on the training data, each hypothesis should also be computable. So given this, we can say, I'm going to introduce, okay, what is a computably enumerably represented hypothesis class? So you can represent it as follows, where H is equal to, so phi I is a function, so a hypothesis, that's computed by the ith program, so it's computable, it's computed by ith program. And WE is basically the computable listing of all of these programs. So this is what it means to be computably CE represented. Now, an oracle. An oracle X is a black box that you can give a program or a computer access to, and that makes the computer more powerful. And then there's this idea of relativization. So almost every definition, proof, theorem in computability theory relativizes to an oracle, meaning you can give it oracles. So you can tell when you're talking about computable functions, you can talk about X computable functions. So that's basically, you can imagine that normal programs or Turing machines are basically oracle programs where the oracle is the empty set. But relativization becomes interesting when you begin to give oracles that are not the empty set, like the halting problem. So then you're considering programs that can solve the halting problem as a subroutine or something like that. So that's kind of where the notion of relativization begins to get interesting. Now, we can also use the notion of relativization and talk about relativizing CE represented hypothesis classes. So if you have that's getting there. Okay, so if you have a CE represented hypothesis class here, and you just pass a bunch of oracles, you can have a CE so this is basically, you get the relativized version of the CE represented hypothesis class. So now, generally, so this is an informal idea I'm getting at, but this is an idea that kind of motivates, is a guiding principle for relativization. And the idea is that if you have a proof for some natural object, then it should relativize, that proof should relativize to the relativized version of the object. So if the proof holds true for H, then that proof should also work for HX. And one more thing, so H is degree invariant if when you relativize it to two different oracles that are equally powerful, so that are Turing equivalent or equally powerful, and then the HX and HY also have to be the same. So now, many natural, especially geometric hypothesis classes are degree invariant. Now, why? Well, let's say if you have some example of such a hypothesis class, let's say the class of all half planes or something. So this condition of being a half plane is independent of oracles. It's not like looking at oracles. So that condition is independent of the oracle, so adding an oracle isn't going to change that. However, the earlier example from Agrawal and others is not degree invariant because it depends on the choices of how you number the formulas and how you number the proofs. And there's no canonical way to do so. Now, we can kind of introduce a theorem. So let's say if you have some some CE represented hypothesis class, which is degree invariant, and suppose that it's PAC learnable for relativized to any X. Then we show that there exists an oracle B such that for all oracles above it, all oracles more powerful than it, H of X is CPAC learnable. And the way to think about that is for all oracles, on the cone above B, h of x is, on the cone above B, it's CPAC learnable. And the way to think about what does it mean to be like CPAC learnable or have some property on a cone where you're saying that property holds for most x. Now, finally, the fun part. Okay, now, using this theorem, we can actually make the an informal argument. So let's say if you have a CE-represented hypothesis class, which is PAC learnable, and suppose it's degree invariant. So it's CE represented in degree invariant. And suppose it's reasonably natural. Remember we talked about like the idea is that if you have an object which is reasonably natural, then proofs for it should relativize. Well then, because it's PAC learnable and it's like natural, the idea is that the proof of it being PAC learnable should relativize. So every hx should be PAC learnable. Now, suppose that h were not CPAC learnable. Well, also because it's natural, this proof of it not being CPAC learnable should relativize, and then therefore you should say, that, okay, it's h of x is not CPAC learnable for any x. However, our theorem shows that there is some b such that for every oracle stronger than it, h of x is CPAC learnable. Therefore, this b bears witness to that contradiction. So, in summary, if you're dealing with a hypothesis class as CE represented, so the computer can like enumerate the hypotheses and actually run the hypotheses. It's a degree invariant and like reasonably natural. Then PAC and PAC learning and CPAC learning coincide. Thank you.
Thank you. Any questions?
Hey. Okay, so maybe I'll preface my question by saying I'm very confused, but what do you mean by natural? Was there a formal definition anywhere?
No. So like by natural, like that's like where, so I mentioned that this is like an informal argument, and this is an informal argument because we're using the idea that that typically natural properties relativize in the sense where, let's say if you define something like a natural way, where basically like if you don't have like a computability theorist sitting and cooking up like a clever counterexample, then like all those other things are unless someone's doing that, then it's like normal properties are kind of considered to be natural, and they tend to relativize. So that's why I was just using that. I said this like an informal argument. Does that kind of make any sense at all?
Okay, kind of, but more literally, no. So, so for example, there's like natural proofs, like there's a formal definition for this.
Yeah.
I'm wondering, is there a way to formalize this natural, or I'm just like kind of confused by the scope of the.
So the way we're using it here, we're not using it like in a formal way, and also I did this work with like another professor Professor Matthew Harrison-Trainer, which couldn't be here right now, and he would be able to answer that question probably better than I would because he dealt with some of that side of things more than I did, but yeah.
Okay, sure. Thanks.
Thanks.
Thank you.
Can I ask another quick question? So just, it's somewhat similar. I'm wondering if you can talk a bit more about what does it mean that there exists an oracle from some point on. Is there any intuition? How should we think about that?
Okay, so let me think about how to make, if I can explain any intuition for a second. So again, this is work that Matthew would be able to explain this a lot better. He did he's done a lot of work around the whole idea of what it means for like cones of Turing degrees and all that.
We can also take it offline.
Yeah, we'll take it offline. Thank you.
Okay, thanks Ed again. Thank you. Okay, so our next speaker is Emmanuel.
This one is the clipper. This one is the clipper.
Okay, so welcome, Manuel.
Hi everyone, I'm Emmanuel and I'm going to talk to you about this work on fine-grained characterization of pack learnability. Okay, this is joint work with this beautiful group of people. And just a brief mention, Max is on the job market. He's a cool guy, so chat with him if you find this cool. So we're going to focus on the pack learning framework. This is well studied. People know it very well, but I'm going to go over it just to be clear on the definitions. So we have a classification problem. So we're given a distribution over x times y. X is the domain. No real assumption on that. And y is the label space. And in this work, we're going to focus on the multi-class classification setting. So y is finite. Now, we're also given a hypothesis class, which is a set of functions mapping from x to y. And we define a learning algorithm as an algorithm that, given a training set, sampled IID from this distribution D, which is unknown, outputs a classifier that performs well. And the performance is classically measured as the prediction error with respect to the 0-1 loss. So the probability of a mistake of the predictor over a fresh test point from the same distribution. Right? And we're going to focus on the realizable setting, meaning there exists a function in the hypothesis class for which this prediction error is equal to 0. We define an algorithm as a pack learner if for any realizable distribution D, when given a large enough sample, it returns a predictor with a small error measured by what's shown there. So you might ask me, okay, we know this already. Why did you go over it again? Because I'm going to generalize these definitions. So in particular, if you look at what people, what happens in practice, there are many situations in which you don't actually just want to look at the 0-1 loss. You actually have more granular costs depending on what you predict and what is actually the true label. Think of it, for instance, here on a medical diagnosis example, where like predicting that a person is not sick while it actually is, can be more expensive than actually predicting it is and maybe having it go over some tests and then finding out later that the guy doesn't really have any sickness. And so we're going to consider costs as something more fine-grained, meaning confusion metrics over predictions, which are the rows, and the true labels, which are the columns. And so these are called cost-sensitive losses. So these are just matrices over pairs of predicted and true labels, and they assign a cost, and we assume, without loss of generalities, value between 0 and 1. And we will define our new performance metric as the expected cost over the test point. So it's much more general than what we looked at in the standard definition of pack learning. And we will also extend to multi-objective losses, meaning we have a finite collection of these cost functions, and we want to look at them simultaneously and try to optimize them. So we will have to generalize, of course, the notion of learner, which here we call WZ learner. So given a list of cost functions W and a list of guarantees Z, what we would like to achieve is that for any realizable distribution and epsilon, there exists a number of examples such that if we feed a sample of this size to this learner, it will guarantee simultaneously for all losses this guarantee Z I plus epsilon simultaneously for all of the losses. So this is much more general than before. Again, first of all, you can clearly see this is a multi-objective problem, not necessarily, but it can be. We look at cost-sensitive losses, and also we don't necessarily aim at minimizing the loss, achieving it a value arbitrarily close to 0, because in general it's not really possible. But we will show that we will also be able to capture partial learning settings. So it's not that we cannot do anything at all, we will be able to still do something. And the goal here is characterizing the learnable region, which is the set of guarantees such that it is possible to learn them through the hypothesis class H. So the first idea that comes to mind is that of randomly guessing the label, right? I just want to throw a die, but I don't want to be too stupid about it. Given like a distribution Q, which think of it as the marginal distribution over the labels in the population distribution, I want to be able to find a distribution over the labels that I can sample from and for which I'll be able to guarantee Zi with respect to the cost Wi simultaneously for all I, right? And if we look at the set of vector Z for which I'm able to do so, we will call them dice attainable guarantees, and these, of course, are trivially learnable. It suffices to just estimate the marginal over the marginal distribution over labels, and I will be able to achieve this. But now I want to be able to actually use the class H and to be able to do much more than that. And we will go through the notion of informed random guessing in a way. So assume that you managed to find out that the true label is actually in a certain subset of the labels. Now, we can do the same argument as before, but notice that I will only need to consider these marginal distributions over labels that have support contained in this subset J of labels. So now we define a set Dj in the same way as before, vector Z satisfying that property there, which we call J that's attainable. And essentially, these sets are the set of guarantees that are learnable whenever we are able to restrict the candidate labels to just the subset J. And we will do so using the class H. These sets are like upward closed and convex, and they will satisfy actually nice properties. Now, we will show that actually these sets will characterize the learnable region in the following way. So for every hypothesis class H and every list of cost functions W, the learnable region is exactly characterized by intersections of these dice regions, right? And we actually have to introduce a combinatorial dimension that is specific to each subset of labels, right? So just to give you an intuition, so this dimension dj is a natural extension of the VC dimension to a multi-class setting. Essentially, what it says is it's defined exactly as the largest integer for which I can find a subset of the domain, and for which the restriction of the hypothesis class over this subset contains all possible functions from the subset itself to the list J. So if J has size 2, we go back to the binary setting, and this is exactly the definition of VC. But you can see this is much more general than that. And when this dimension is infinite, essentially what this tells us is that we cannot breach the boundary of the dice region dj. And so this will constitute, and this will be true for some lists of labels, and but not necessarily for all of them. Hence, why we intersect over all the lists J that have this dimension infinite, because essentially all of these are boundaries that we cannot really breach. And actually, we show that this is an exact characterization. We also have lower bounds that tells us we cannot do better than that. And yeah. So this is an exact characterization. We actually have to use a refined variant of the one inclusion graph to achieve this. And also have some sample complexity guarantees. And let me just briefly go over them. The sample complexity guarantees are roughly optimal. They're just missing like a 1 over size of the least factor. And in particular for the learning problem, we also have an additional 1 over epsilon squared in the sample complexity, which we believe is not necessary. In general, you would argue this is a realizable setting, so it wouldn't be there. And this is a nice open question that we didn't address yet. And it's due to the fact that we actually have to estimate the margin over the labels in the multi-objective setting. This term is not there in the single objective, but I think this is a nice open question to address. And also, we have a specialized analysis for the population-driven losses, which is like a special case of losses that look at, like in the binary setting, essentially go back to the false positive and false negative errors, and you try to optimize them simultaneously. But these are much more general, and we show improved sample complexities for them. Okay, thank you.
Thanks, Emmanuel. Any questions?
Thanks for the talk. So you mentioned in the beginning that you're doing realizable case. What would happen in unrealizable case?
Okay, so we didn't really look into that, but essentially this will probably require different techniques. We would expect that, essentially what we do here, okay, I didn't go over this because of time constraint, but this dimension come out of a specific problem that we look at, which we call pack elimination. So pack elimination is a problem that is specific to a subset of labels, and what it says is essentially that your loss is not just the 0-1 loss, but it's you incur a loss of 1 whenever you either predict a label that is not in a list J, or when it's the true label. So this essentially tells you, am I able to, given knowledge that the label is in J, am I able to eliminate one label that is not the correct one, right? And we studied this problem in the realizable setting. I think that in order to look at the agnostic setting, you would need to study this problem in the agnostic setting itself, and then use our reduction from this problem to the more general learning setting to see what
in your case, realizable means that you achieve 0 error along all these sort of problems.
Yeah, exactly. And essentially, it's not always the case that you can also yourself achieve cost arbitrary equals to 0. You will have these boundaries, and this is unavoidable, and it depends on the richness of the class H. Right.
Thank you.
Okay, so let's thank the speaker and move to our last talk, I think. Our last talk this session, but okay.
That should be me. This right here?
This is for the light. This is the clipper, I think.
Which one's the clicker?
Yes.
I see. Okay. No, it doesn't. It's not working.
This one? So.
I think probably this one. Okay, yeah, that's good. Yeah, no worries.
Okay, so our next speaker is Shahadin. Welcome.
Thank you. Someone forgot their phone up here, I think.
I'll wait.
Okay. Is this the microphone? Testing. Okay. My name is Shadin. I'm going to tell you about work that is. Oh, sorry. Yes. Yeah. Oops, sorry. Okay. So this is primarily the work of Sky Jafar, who, believe it or not, is a high school student. It's also joined with Julian Estilis, who many of you know, who is a PhD student at USC. Okay. So I'm motivated by the search for algorithmic templates for learning. I want them to satisfy 3 properties. I want them to be simple, I want them to mirror the successful templates we see in practice, and I want them to succeed at learning whenever learning is possible for many kinds of problems. So one success story we all know about is empirical risk minimization. This is where you minimize the training error. You pick a hypothesis in your class that minimizes error on the training data, capital S. Obviously, this is used a lot in practice and has a lot of theoretical evidence that it succeeds for many problems. Another success story is structural risk minimization. You might have heard it referred to as regularization. This is where you trade off the empirical error with some measure of model complexity, which I'm calling psi of h here. Okay, this function psi is what we call a regularizer. It measures the complexity of the hypothesis. So this could be L2 or L1 in regression, for example. Okay. And again, there's a lot of theoretical evidence that structural risk minimization is successful for large classes of problems. So ERM and SRM, however, can fail to learn when you go beyond a small number of labels or low-dimensional labels, even for problems that are learnable. And this can be seen in multi-class classification, where you can have problems that are learnable but by different styles of algorithms. There are general-purpose multi-class classifiers. I've listed some here, but they're usually based on more complicated templates, like orienting one-inclusion graphs, sample compression, and list learning. So I would argue that they violate Desiderata 1 and 2 up there. Okay? So then this brings me to my question, what's the right algorithmic template for multi-class classification? One candidate that I'm going to talk about today is what's known as local regularization. Also, we call it sometimes local SRM. You're given your training data, and you're given a test point, and then you choose the hypothesis that trades off training error with a regularization term, but now the regularization term depends on where your test point is. So this function psi now takes the test point also as an argument. So I call this psi a local regularizer. How should you think about this? So the idea here is that different hypotheses can be simple or complicated in different areas of the domain. So if you look at this picture here, the orange hypothesis is complicated on the left, simple on the right, and the blue hypothesis is vice versa. So if your test point is on the left, you might prefer the blue hypothesis, all things being equal, and if your test point is on the right, you might prefer the orange hypothesis. Okay? All things being equal, of course. The nice thing about this template is it can give us improper learners through this dependence on the test point, and this is necessary for some learnable multi-class problems. And we were also surprised and happy to find out that local regularizers have actually appeared quite a lot in the theory and the practice of machine learning. I have citations in the paper if you're interested. Sometimes they don't call it that, but that's actually what's going on. Moreover, we proved the last colt that if you augment this template with some unsupervised pre-training, you can actually learn all learnable multi-class problems. So there's like a lot of evidence that this could be a promising candidate. But one question we left open last colt is whether local regularizers in this vanilla form, without any pre-training, whether they can actually learn all learnable multi-class problems. So that's the problem I'm going to tackle in this talk. So we have a negative result. We show that there is a realizable multi-class classification problem, which is learnable, pack learnable, and also transductive learnable, for those of you who know what that is. But it's actually not learnable by any local regularizer in the transductive model. I'm going to tell you what the transductive model is momentarily. Okay? One thing that's interesting about this is to prove this result, we had to modify the first Cantor class, for those of you who are familiar with this. That's a class due to Danieli and Shalev-Schwartz, using an interesting construction from cryptographic secret sharing. Our negative result is for the transductive model, but we think it should actually also hold for pack learning. It's just that our proofs didn't generalize. Okay? But let me tell you about this transductive model and why you should care. This is an early model, a model from the early days of learning theory. Here, instead of distributions, an adversary actually chooses a labeled data set, a realizable labeled data set. And then one of the labels is omitted uniformly at random. Let's say yi is omitted. So you have x1, y1 through x and yn, except for yi. Yi is chosen by nature uniformly at random. And then the learner must predict this omitted label. So this is kind of a game of fill in the blank, basically. This is intimately related to the pack model, it turns out. Learnability is equivalent in both models, and the sample complexities are basically identical up to low order factors. And moreover, all multi-class learners that are general purpose, multi-class pack learners actually factor through this transductive model. So this seems to be the only general tool to kind of get to multi-class learning. Okay? So given that these things are closely related, we actually also conjecture that the same multi-class problem we design is actually also not pack learnable by a local regularizer. And I hope someone works on this problem. It's actually a very good problem for a PhD student starting out. So I highly recommend this as an open problem. Okay. But we proved this impossibility for the transductive model, and now I'm going to tell you a little bit about our construction. Okay. So we start with the first Cantor class of Danieli and Shalev-Schwartz. Here you have a large domain, say everything in this circle. And then your labels are subsets of the domain and also the special symbol star. Now for each subset of roughly half the domain, it basically splits the domain down the middle. I'm going to create a hypothesis that labels points in that set with the name of the set, otherwise labels the point with a star. Okay? So this is self-referential, hence the Cantor association. Right? Proper learners will fail on this class. If your distribution is uniform over the star region and your domain is large, you really can't learn much about this decision boundary with a proper learner. You're bound to kind of output an almost unrelated decision boundary, so you will get constant error. But there's a simple improper learner. If you see the non-star label A, you've basically identified the class and you're done. But if all you see are stars, it's safe to predict stars for everything. So you can use this all-star hypothesis, which is not in the class, hence the improperness. And also, this learner can be witnessed as a local regularizer by having each test point prefer hypotheses that label itself as a star. So we're going to have to modify this class to obstruct local regularization. My modification is going to involve secret sharing. Let me give you a quick primer on that. You have a secret string C. You want to distribute it among two players so that neither player learns anything on their own, but they can work together to reconstruct the secret. There's a simple scheme for this via the one-time pad. You can just sample two random strings conditioned on their XOR equaling the secret. So neither the players learns anything, but they can XOR their secrets together, XOR their shares together to get the secret back. So based on this setup, we can create a hypothesis for every setup like this, where the strings are indexed by the points in the domain, and the secret determines a partition of the domain down the middle, and then one of the sides goes to player 0, and one of the sides goes to player 1. And then I label the points in each side with the name of the player and their share of the secret. So 0, A is the label for the points in player 0's side, and then A is player 0's share of the secret. And similarly for player 1. So this is also learnable like the first Cantor class, where if you see both labels, you can XOR the secrets together and learn the hypothesis. But if you see one label, you can just predict it for everything. But it's not clear how to witness this as a local regularizer because my default label is not this star, but now it's context dependent. It depends on the training data, and it's not clear how to encode that in point-by-point preferences over hypotheses. So we formalize that into a theorem, and we show that every local regularizer has error at least a quarter on this OTP class in the transductive model. I'm going to skip most of the proof because of time, but essentially we exploit the symmetries in this class, the label symmetries in this class. We show that to get everything right, you have to have a lot of cycles in your preference order, cycles of length 4. We have to break 1 out of 4 to get the correct labels. But getting this to work involves like an intricate probabilistic coupling among transductive instances. Okay? So to conclude, I ruled out local regularization as a general approach for multi-class learning in the transductive setting, using a secret sharing construction, modifying the first Cantor class. We had to use properties of the transductive model to get our proof to go through. The transductive model has a nice one-to-one correspondence between training and test points, which we really exploited to get a handle on what the learner must do. I think this should be more general if you just have better proof techniques. So my conjecture is that this same class is not pack learnable by any local regularizers. But if this conjecture is false, I would say even better, because we would get a surprising pack transductive separation. And that's all I have.
Thank you. Any questions? Okay, so if nobody, so I'll ask one. So what goes wrong when you try to extend the lower bound to pack? Like,
when you try to extend the lower bound to pack, there's many hypotheses you could output that would kind of move sideways in the order So you don't really have, you can't really constrain the learner as much. You can't really have as tight a constraint on the order of the learner. We go in depth in the paper about all the obstacles.
Okay. Okay. Thank you very much. And let's thanks Shadeen and all the speakers. Yes, thank you.